Stanford University.
I say, okay, let me read to you from the first paragraph. Statistical mechanics is often thought of as a theory of how atoms combine to form gases, liquids, solids, and even plasmas in black body radiation. But it is both more and less than that. Statistical mechanics is a useful tool in many areas of science in which a large number of variables have to be dealt with using statistical methods. My son, who studies neural networks, uses it. In fact, about 6 months ago, he called me up and says, hey, Pop, do you ever hear of this thing called the partition function? And yeah, I heard of it. And he said, I'm just learning about it now because we use it in the statistical properties of neural networks. Free energy, all those concepts that one often thinks of in the context of physics, but it's a much broader set of ideas than that. So let me just continue with reading. I have no doubt that some of the financial wizards at AIG and Lehman Brothers used it. So that was just to reinforce what you asked me about derivatives. Right. Saying that statistical mechanics is the theory of gases is rather like saying calculus is the theory of planetary orbits. Really what it is it's a mathematical structure. It's a mathematical structure which of course has applications. And if I had to put it in a nutshell, in a very brief nutshell, statistical mechanics is simply probability theory. Now, I personally have never understood the difference between statistics and probability. I'm so told there's some technical difference. I guess there probably is, but I don't know that difference. But statistical mechanics is the application of probability. Well, statistical mechanics is probability theory. It may be applied to lots and lots of different situations, but it's probability theory under certain specific circumstances. So I want to talk about those circumstances a little bit first.
As I understand it, yeah. The statistics is the purely mathematical part that it doesn't depend on whether or not the mapping to reality connects. So with probabilities, you are trying to do something where you're predicting behavior of something.
Okay, so if you're right, and I have no reason to think you're not, and I understood exactly what you said, statistical mechanics is a mathematical structure. Okay, so I suppose in that sense it's statistics. The question is, under what circumstances does it apply to reality? And I want to talk about that a little bit, but the real answer is very, very difficult. And I think, to my knowledge, it has never been completely sorted out and proved in absolute rigor that statistical mechanics, as we define it, actually applies to any serious significant system other than some very simple model systems. But it's interesting to think about what are the criteria and what are the circumstances under which statistical mechanics, as we normally think about it, applies to systems like a piece of chalk. Let's hope, pray. Good. It works. So let's start with coin flipping. Coin flipping, you have a coin which has heads and tails, and ordinarily, under ordinary circumstances, you would say that the probability for flipping a head is a half, and the probability of flipping a tail is a half. They have equal probabilities, and the probabilities sum to 1, so therefore it's a half and a half. What right do you have to say that? How can you prove that? Well, one simple argument, which is rather convincing, is that coins are symmetric, apart from some little detailed differences between the two sides of the coin. And in fact, of course, because of the difference between the two sides of the coin, it's not absolutely true that the probability is a half and a half. one side may weigh a little more. You know, the mass distribution is slightly imbalanced because on one side the carving is a little bit different than the other, but forget that.
Air resistance.
Yeah, air resistance could have, but if the coin was a really fair coin, it means that it's so symmetric that you, for the purposes of flipping the coin, the two sides are exactly the same. Somehow you can look at it and tell which is which, that's true. But the paint that distinguishes the two of them is so thin, or the carving or whatever, that it doesn't make any difference. The symmetry between the two sides of the coin ensure that the probabilities have to be the same. And once they're the same, it has to be a half, right? Okay, so that's straightforward. There's a kind of notion of a priori probability. A priori probability, in this case, because there is asymmetry. Let me give you another example. Let's take a die. Die is in dice. And let's color the faces of the die. I want to color them rather than number them for no important reason. All right, so there are 6 sides to a die, and let's color them red, yellow, blue, green, orange, purple. Okay. Now, again, the 6 sides of the coin, not the coin, the 6 sides of the die are symmetric. There's a symmetry operation of just turning the die through 90 degrees about various axes, which takes any configuration of the die into some other configuration. And that symmetry, again, ensures, if you believe that the die is really symmetric, if you believe that the die is symmetric enough, then you're forced to believe that the answer is that the probability of getting a, let us say, red, or any other one of the colors, is 1/6. Right? And that's a good argument. But in most situations, there aren't such symmetries. So if there aren't such symmetries, is there a notion to back you up from where you can start, your starting point for a discussion of probabilities, a starting point which you can think of as a priori probabilities? The answer is not obviously, but let's talk about it a little bit. In particular, let me give you a ridiculous kind of example. Let's suppose I decided to take the die and color it by replacing purple by red. It now has 5 colors: red, red, yellow, and so forth. It now has 5 colors. Now, if I just write down the 5 colors and you stare at them, you would have no reason to believe that there's not a symmetry among them. Just writing them down one after another. Of course, one has more letters than the other, but that's not the point. You could number them if you liked. You might say, look, I have 5 possibilities: red, yellow, blue, green. Oh, there it is, green and orange. So what's the probability of flipping a red? And the answer, by the same logic, or illogic, would be 1/5. But you know perfectly well that's not the answer. Yeah.
Can't information theory make this rigorous by defining the entropy functional?
Well, we're going to spend a lot of time doing exactly that. But no. In principle, yes. But in fact, systems are too complicated to easily prove that the conditions for thermal equilibrium and so forth really apply. Most systems are too complicated. There's a few model systems that you can actually prove the theorems about, but in principle, you can state the conditions, but it's very, very hard to prove them. In any case, here you have 5 colors. And if you didn't know any better and you didn't know very much about the die, you would say that's 1 in 5. But of course, the answer is not 1 in 5. The answer is 2 in 6 for red and 1 in 6 for yellow, blue, green, and orange. So what's going on? Well, the answer, of course, is that the real symmetry of the system acts on the 6 faces, not on the 5 colors. But it's very easy to imagine that a die doesn't have a symmetry, doesn't have any symmetry at all. It could be weighted in some way that's sort of off balance. It could be an unfair die, weighted with extra weight in one corner or something like that. And then where would you get your a priori probability from? Well, of course, one way of getting the a priori probability would just be to flip it a zillion times, and after a zillion flips, you could count how many of each kind you got. But that's not what we're going to do. We're not going to try to study this air in this room by doing a zillion replicas of the room. I mean, we will do that mathematically, but not physically. And so someplace else we have to get the basic ideas of a priori probability from. You might go back a step and say, if the die is not really a fair die, then the probability is going to depend, or may depend, on all kinds of things. It may depend on details such as the way the hand flips it, the air currents in the room, the nature of the surface that it may or may not bounce off, all kinds of details which are extraneous to the system itself. In other words, it may depend on the environment as well as the system. So the idea of an a priori probability for the die may not be such a good idea after all.
You haven't mentioned the fact that you've implicitly assumed a time symmetry in which you can repeat.
We are going to implicitly assume time symmetry, and in fact, we're going to talk about that sort of right now. Let's add a dynamical element to the idea, which may help us get a handle on this idea of a priori probability. The cube here, the die, let's think of it as a dynamical system. A dynamical system means one which changes with time under some law of motion. A law of motion is simply an updating process. It tells you if you know the state of the system at one instant of time, it tells you what the state will be in the next instant of time. That's the idea of a law of motion, an updating from one instant to the next. Now, of course, with the motion of particles and things like that, the motion is nice and smooth and continuous, and you can subdivide the time into infinitesimal elements. But if we're talking about a die, the closest thing we could imagine to that is that the die executes operations one per what? Per elementary time interval. In other words, we imagine dividing up time into equal segments. We will not take the limit. And at each instant, the die rearranges itself in a way that only depends on what's showing at the top of the die. Okay, so we could represent that law, and in previous versions of this class, we have talked about this kind of thing several times. But you can represent the motion of the die as a rule. Okay, so let's see, I have some rules written down here. Let me give you some rules. Here's the first one. If the top of the die is red, then in the next instant, let's see, where is it? Red goes to blue. If it's blue, blue goes to yellow. If it's yellow, yellow goes to green. If it's green, green goes to orange. And if it's orange, orange goes to purple. And if it's purple, purple goes back to red. We could represent this as a kind of diagram. We could put the 6 colors down: red, blue, yellow, green, orange, purple, and then just draw some arrows. Red goes to blue, blue goes to yellow, yellow goes to green, green goes to orange, orange goes to purple, purple goes back to red. Okay? That would be a complete dynamical theory of a very, very simple system, the die. Okay? Now, supposing the motions occurred quickly. Let's suppose they happened fast. So fast that they happen, let's say, in less than a blink of an eye. And now we ask, I don't care whether the die is weighted funny or not weighted funny. It doesn't matter. This is the rules. This is the rules of motion of the die. And it spends equal amounts of time at in between each successive motion. Then it's pretty darn clear that if I just randomly sample it at an instant of time, as it's going from one to the other very fast, if I randomly sample it, it's pretty darn clear that I will have an equal probability of getting any one of the 6, 1, 2, 3, 4, 5, 6 colors. Right? Just because they each spend the same amount of time, or the die spends the same amount of time being in each one of these states. So it's pretty darn clear, I don't think I need to prove it, that this would be a situation in which the probability would be 1/6, as you would expect. Now, this is fairly robust. We could replace this law by other laws. Let's see, I have another one. I think I have 2 others written down. Well, we could just replace blue by green and green by blue, and maybe change some other ones. Wouldn't make any difference. So there are many possible laws like this, all of which would lead to the same 1/6. So it's fairly robust in a sense. But is it completely robust? No. I'll give you an example of a law which gives a different answer, or it doesn't give an answer altogether, really. That's the point. Okay, so here it is. Red goes to blue. Blue, let's see, what do I have here? Blue goes to green. And green goes back to red. Yellow goes to purple. Purple goes to, what have I left out? Orange. And orange goes back to yellow. All right, now at every stage, whatever the state of the system is, it tells you what to do next. There's nothing wrong with this rule. It does have a funny property relative to this one over here. What is that funny property? Well, maybe the easiest way, it has 2 orbits. This has 1 orbit, this has 2 orbits, or 2 cycles. You might say cycles. In fact, if you graphed it, you might red, blue, green, back to red, and yellow to purple, to orange, back to yellow. 2 distinct cycles. Now, there's no way a priori to know what the probability is that you're on this cycle or that cycle. If you're on this cycle and you know you're on this cycle, and you whip around it real fast, then obviously the probability is 1/3 to be red, blue, or green, and 0 to be yellow, purple, or orange. But on the other hand, all you may have is also statistical knowledge, where it came from, let's not worry about now, about whether you're on this cycle or this cycle. And that, in that case, it would be more complicated. I'll leave it to you to calculate if it was, of course, if it was a half, probability of a half for this and a half for that, then you would reduce yourself back to 1/6. But if it was probability 1/3 to be on this cycle and 2/3 to be on that cycle, then it would be more complicated. I'm not going to work it out right now. Okay, so this is a counterexample to the statement that there's equal a priori probabilities for all configurations. But this system, or with this law of nature, this law of motion, there is something called a conserved quantity. All right? Let's define a quantity Z. Z is for zilch. This is the zilch. The zilch has a value either 1 or 0. It's equal to 1 for red, blue, or green, and zilch is equal to 0 for yellow, purple, or orange. Two distinct orbits with two distinct values of the zilch. The zilch is conserved. What does it mean that it's conserved? If it starts at a particular value, it stays at that value endlessly. So a conservation law, in this context, and really in all contexts, means that the system breaks up into different orbits with different values of the conserved quantity. There may be many conserved quantities for a complicated system, and you have two possibilities. One is to fix the zilch. You measure it. You know what it is. If you know what it is, then you just throw away all the other values, and you go back to a somewhat smaller system, in this case a system with 3 states, but just repeat the story, and there will be equal a priori probabilities of all of the states with the same value of the conserved quantum number, with the conserved quantities. And as I said, the other possibility is you may only know statistical information about these things, in which case you use that statistical information, but statistical information about the values of conserved quantities. What's the most important conserved quantities in physics? Well, energy is going to be the most important one for us. Momentum is not going to play such a big role. And the reason momentum doesn't play a big role is because usually we're thinking about systems which are contained within containers. In statistical mechanics, we're usually thinking about gases or liquids or whatever it is contained in containers. And of course, when a molecule hits the wall, it bounces off. Of course, it gives a little bit of momentum to the box, but we don't care that much about the box. We don't try to keep track. If I throw a tennis ball against the wall, we don't have to remember that the earth recoils a little bit. It doesn't play any role in what goes on with the tennis ball. It's not important. And so if we ignore the recoil of the box, then momentum is not conserved by virtue of hitting the sides of the box. So momentum is not so important. Electric charge can be a very important conserved quantity. Angular momentum is much like linear momentum, also tends not to play a big role in general, but it could. I mean, it could under certain circumstances. So the rule is you take, or a simple rule would be, you take all of the conserved quantities, and you fix them. In other words, you measure them, or some other way, you know what they are. And then you simply study the system subject to the constraint that the conserved quantities have certain values. Okay? That's essentially the structure of statistical mechanics. Calculating probabilities of things subject to constraints, and those constraints usually take the form that some quantity is fixed. Some conserved quantity is fixed, one or more. All right, let me give you an example that we could make up using dice, one die. No, well, okay. Let's make up an example involving 2 dice. Now I'm going to number the sides. 1, 2, 3, 4, 5, 6. Of course, this one also has a 4, 5, and a 6, but you can't see it. And this one also has a 1, 2, and 3, and you can't see it. And the rule is now they interact with each other. Interacting with each other means that when one flips, the other is also forced to flip. And the rule is they flip in such a way that the sum of the numbers on the 2 of them doesn't change. For example, in this case, we start with 2 and 6. From 2 and 6, we can flip in a way that can bring us to what? It can bring us to 4 and 4. It can bring us to 1 and 7, except there is no 7. It can bring us to 3 and 5, but it cannot bring us to 1 and 2. So that's a rule, and we could write that as a conservation law. For each value of the total number, there would be another closed cycle, because you can't get off the cycle. You can't change the total. I don't know what to call a number here. That's another generalized zilch. The generalized zilch here cannot change, and so therefore let's see, how many possibilities are there for the conserved quantity? You can have 1 and 1, you can have 2. Conserved quantity can be 2, it can be 3, and what's the largest value it can have? 12. Okay.
Then it'd have to be 7 in order to have any, well, if it was 7, then you could, any 1, 2, 3, 4, 5 would match, and subtracted from 7 would give you the other.
No,
You'd be able to use all sides of it.
2 is just very constraining.
2 is very constraining. Yeah, there's only one configuration. As it happens, there's only one configuration.
Could you argue there's 2 because there's 2 dice?
No, they both have to have 1. That's one configuration. This one being 1 and this one being 1.
You have like 11 where one's 5 and the other's 6, then they switch.
That there are 2.
There are 2 ways of making it.
Yeah, there's 2 ways of making 11,
We are assuming
but only one way of making 12. Right.
rotational symmetry.
No, okay. Just the only thing that counts is the number on top. All right, you get the point. All right, so I haven't told you what the multiplicity of each value is. This only 1 here, only 1 here, one configuration. Here, what's a 3? You can do with a 1 and a 2 or a 2 and a 1. I think those are the only 2 ways. Is that right? Right. What about a 4? I think that's right. So there's a multiplicity of ways of doing it, but each one of these numbers has associated with it a cycle. Let's, for example, the 2 cycle. The cycle associated with 2, what is that? Yeah, you know, okay. Yeah, 1, 1 goes to 1, 1. That's all that can happen. It just stays, in other words, it stays the same. Stays the same. What about the 3? How many possibilities are there for the motion within the 3 cycle? What are they? Let's see. 1, 2 goes to 1, 2. Or 1, 2 goes to 2, 1. Okay. Both of them are possible. So I think there's two, yeah, so I think, what do we say? Oh, sorry. This is the 2 cycle. There are 3 states of the 3 cycle. What are they? What? No. 2 states of the 3 cycle. Yeah, yeah. So it's one of these jobs like that. One goes to the other comes back to it. 2 possible cycles, or you just come back to the same thing. Okay, one of the other. And so forth. There are a bunch of different disconnected orbits. The orbits, in this case, would be characterized by the value of this number. And once you fix it, then you can throw away all the others and concentrate on the little subsystem which is which has a particular value of the conserved numbers. All right, is that clear? All right, the most important quantum, I keep saying quantum number, the most important conserved quantity is energy. And that's the one where most of our focus is going to be. There are others. For example, in chemistry, there are a lot of conserved things. The amount of each, or the number of atoms of each, element are conserved in chemistry. Okay? In nuclear physics, of course, that's not true, but the total number of protons plus neutrons is conserved. So there are other conserved quantities, but as I said, for the most part, energy will be our most important. Sorry. Let's go back a step. Let's go back a step to information. Information plays a very important role in what's going on. I gave you a counterexample to the robustness of this, namely the existence of conserved quantum numbers, conserved quantities, but obviously it's not really a counterexample. You just have to generalize a little bit. But let me give you now an example which is really much worse. And the much worse example goes like this. Red goes to red. Yellow goes to red. Blue goes to red. What do you think green goes to? Red. Orange goes to red. Is there another one? Yeah, blue. Blue goes to red. Oh. Yeah, but purple, good. Purple goes to red. That's a perfectly good deterministic law. It tells you what happens next. No matter where you start, you just get red. All right? You start the system out somewheres. Okay? There are no conserved quantities here. No conserved quantities. There couldn't be. If there was any conserved quantity, it's very quickly, there's obviously no conserved quantity. They all have the same value, because or whatever quantity you pick, because they can all get to red. So they have to have the same value of whatever it is as red does. So there's no conserved quantity. That's not the problem here. On the other hand, it's certainly true that at least over reasonable lengths of time, remember this thing happens fast, blip, 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 blip. If you intervene with a system, what's the most likely thing that you find? Red. In fact, not only is it the most likely, it's overwhelmingly more likely. It's infinitely more likely. You will simply find red. You won't find any of the others. Here's an example where there are no conserved quantities, but it is not true, nevertheless, that there is equal a priori probability of all of the different values of the color index here. All right. What's wrong with this example? Well, there's nothing really wrong with it. It's a possible world, but it doesn't behave the way real dynamical systems do. Real dynamical systems have something that I always call the conservation of information, but you could equally well call it the conservation of distinctions. What it says in this simple context is that distinctions between configurations don't disappear. Distinct beginnings always give you distinct outputs. Distinct starting points always give you distinct outputs. And not only that, if you trace backward, first of all, it's deterministic, which means no matter where you start, you get to a very definite place after each instant. And distinctions don't merge. In other words, what this would look like would be red goes, well, let's see how to draw it. Red goes to red, yellow goes to red. Obviously what happens here is the different trajectories all merge. They all merge and come together with red. No matter what you start with, red, yellow, whatever, you get out red. So in this case, the trajectories just merge together, and because they merge together, initial distinctions are lost. You can call that loss of information, you can call it loss of distinctions, you can call it the violation of the conservation of information.
How about irreversibility?
You can call it irreversibility, but irreversibility, it is a form of irreversibility, but I don't want to confuse it with thermodynamic irreversibility. Thermodynamic irreversibility is a different thing, so I didn't want to call it that. But it's sort of the deepest form of irreversibility. Laws of physics which lead deterministically to outputs, but the output doesn't determine the input. You can't get back to the input. Loss of information. In this case here, it's quite obvious that that the a priori probability of the different starting points is not equal. So that's is not equal. The initial, the a priori probability. So that's another counterexample, and that's a more dangerous kind of counterexample. Dangerous in the sense that if you had a system like that, it would not satisfy the rules of statistical mechanics. The rules of statistical mechanics are fundamentally based on the idea that the microscopic laws of physics, the laws of physics which govern at the deepest level, and we're going to be mainly talking about classical physics here, at the deepest level, the molecular level or the atomic level or the elementary particle level or whatever level we have to get to understand the system, that the laws are consistent with the conservation of distinctions or the conservation of
Are we saying that the sample size is not going to change?
the sample size is not going to change. No.
Okay.
If you mean by the sample size, the volume of a system, no. You can say, yeah.
Can you describe this as saying as a one-to-one function?
Yeah.
Yeah. That's
Yeah.
the way to
Yeah,
take that.
you can.
Is this going to be a strong restriction?
Absolutely. Without it, we would get nowhere.
And what about its physical? Is it a good physical assumption?
Yes. It's not only a good physical assumption, it's a consequence of the basic principles of classical mechanics and all classical physics. All classical physics is dependent on it.
So does that mean that if you're outside of the realm of classical ability?
No, there's a quantum mechanical version of it. There is a quantum mechanical version of it. In classical physics, it's called Liouville's theorem. I'm going to tell you what it is. In quantum mechanics, it's called unitarity, but we're not going to be doing very much quantum mechanics. If we do any quantum mechanics, we'll probably do some, but we'll do a sort of seat of the pants. We won't use the real principles of quantum mechanics, but the classical version of it, I will basically tell you right now.
I have a question.
Yeah.
So that's either way, right? One can't go to two different states.
Yeah, I mean, as somebody said back there, the conservation of distinctions means that the mapping is one-to-one.
So that example of the summations of the die is not allowed.
Oh, yes, the summations of the...
Well, because
that may or may not.
Because one state of 1, 2, that could go back to the same state, it could go to a different state.
You have to postulate a law, all right? Now, if in each sector means each value of the conserved quantities, if the diagram in that sector is a closed loop like that, then you're in business. That conserves distinctions. If you start here, you get to here. If you start here, you get to here. You can tell not only where you're going, but where you came from. That's the characteristic of a system which conserves distinctions. If you know where you are, you not only know where you're going to be next, but you know where you are last. Okay? Now, in this case, if you know you're at red, you can ask, where am I going next? The answer is red. Where did I come from? Beats me. I don't know. No way to tell. So, yeah.
You started off by talking about coin flipping, and this seems to be going quite a different way. We're not talking about random outcomes of something. We're talking about quite deterministic rules.
Yes, we're talking, yes, the world, at least the classical world, is deterministic. It's only apparently statistical. It's apparently statistical, and we're going to talk about the conditions why it is apparently statistical. But I will tell you right now, a system is apparently statistical, typically because it's coupled to a much, much bigger system about which you know very little. And a heat bath, in other words. And you don't know enough about the heat bath to specify the details of it. But that's always the case. I mean, that things are random, not always the case, but it's the case in classical physics that things are random, not because there's any intrinsic randomness in the laws of physics, but because you simply don't know enough. You don't specify. We're going to talk about that. That's the basic idea of entropy. All right, in any case, this principle of the conservation of distinctions is so important. It's rarely mentioned because it is so deeply assumed by everybody who does classical physics that it is rarely mentioned as one of the laws of thermodynamics. I would call it the zeroth law of thermodynamics, except the zeroth law of thermodynamics is also used for something else. So we could call it the minus first law of thermodynamics. And it is the most central fact that must be true for thermodynamics or statistical mechanics to make sense, and for it to predict the consequences of thermodynamics, the theory of heat. So it's as I say, built into the structure of classical mechanics. What is the relevant statement about classical mechanics? Classical mechanics, of course, does not deal with these very, very trivial. I use these as illustration of a concept. But of course, classical mechanics deals with continuous systems, systems of coordinates and momenta. For our purposes now, momentum can just be mass times velocity. And each coordinate of a system has associated with it a momentum, namely its time derivative times the mass of the object. But of course, there is a deeper, more profound meaning to the idea of a momentum. We've talked about it in classical mechanics. For the purpose of this class, momentum can just mean conventional momentum. Although there may be situations where you want to keep track of a more profound definition of momentum. All right, so what is the state of a system? The state of a system for this simple example of a single die was just a label color, state the color. If you know it, and if you know the color, you know it comes next and you know it comes before. If it's a case of two dice, then it's a pair of, the state of the system is labeled by a pair of colors. What about a single point particle? A single point particle is labeled by a collection of coordinates, x, y, and z, or x1, x2, x3, x, y, and z. Those are the coordinates of the particle, and the corresponding momentum, the x, y, and z components of the momentum. Equivalently, the x, y, and z components of the velocity. But for reasons that go into the depths of classical mechanics, the momenta are the right things to describe it by. The symbol for momenta, the historical symbol for momentum is p, and the historical symbol for coordinate is, of course, x. There are 3 p's and 3 x's for each particle, so I draw it as just a p and an x plane. But of course, for an ordinary particle, there would be a 3-dimensional p space and a 3-dimensional x space. So it gets complicated fast. To picture the phase space, this is called the phase space. The phase space of a classical particle is 6-dimensional. What is the x space called? Just x by itself without worrying about p. It's called a configuration space. So the configuration space is the space of x's. The phase space is the space of x's and p's. But what constitutes a state of a particle is not an x, but an x and a p. And the reason is that in order to say where a particle is going to be next, you not only have to know where it is, but you have to know how it's moving. Okay? You have to know both its position and its momentum, or the position and velocity. So for a single particle, the x's and the p's are like the color of the edge of the surface of the dice. It labels a state of the particle. For a many-particle system, there are many x's and many p's. If there are 10 particles, how many x's are there? 30. X, y, and z for all 10 particles. px, py, and pz for all 10 particles. So what do we say? There were 30 x's, 30 p's, so for 10 particles, 60 coordinates to the phase space. And so it gets complicated fast. For a system of 10 to the 23rd particles, I won't try to draw it. It's 6 times 10 to the 23rd dimensional space. But now, what does it mean to say, well, first of all, what is an orbit? What is a history? A starting point, which could be like the analog of starting with red, is just a starting point in this phase space. And then the equations of motion, either Newton's equations or whatever equations are governing the system, allow you to follow it. So you follow it with time. These little ticks here could be microseconds. But of course, the motion is continuous, but you could nevertheless, you could divide it up into microseconds if you like, or what's smaller, nanoseconds, or whatever you want to do, and draw the trajectory. And that's the trajectory in the phase space. It's not the trajectory of the object in space. It's the trajectory through this phase space. Wherever you start, there are various kinds of situations, and we can talk about them. In some of them, the trajectories just wander off and go to infinity. For example, just for a free particle, if you give it a shove, it just goes off to infinity. Its momentum doesn't change, so p is constant, but x just goes off to infinity. But for the kinds of systems we're interested in, the systems which are contained within finite boxes, as a rule, the system will not leak off to infinity, but it will somehow usually wind up coming back, or perhaps not coming back to exactly the same point, but that's a bad drawing. That's not a good drawing, because it illustrates something, exactly the thing which doesn't happen. It illustrates exactly. The problem is 2 dimensions is too low a dimension to draw a good picture. Okay, what doesn't happen? What doesn't happen, and now this is a theorem of classical mechanics, and it has several pieces to it. The first statement is that trajectories don't merge. Never happens. All right? This is the analog of saying that distinctions are preserved. Distinctions are conserved. The 2 different starting points never lead to the same endpoint. Okay? And also the opposite is true. Of course, this wouldn't make any sense at all. A given starting point splits in 2. What on earth would that mean? You start at some given starting point, and that would mean it's not deterministic. It would mean you don't know where you go next when you get to this point over here. Those things don't happen. Trajectories don't cross. Number 1, they don't cross. And number 2, they don't merge. So a trajectory doesn't cross like that. They never do that. And they never merge. Now, there can be conserved quantities. In other words, the trajectories can be labeled, for example, with values of energy. The energy doesn't change along a trajectory. It's much like the zilch. It doesn't change along the trajectory. And so the different trajectories in general, whatever they do, may be labeled by the energy. And that energy doesn't change. You pick it once and for all, and it stays that way. So that's, again, what is that called? That's called the conservation of energy. Yeah.
Does the orbit include what happens if you go back in time also?
Yeah, well, of course, that's up to you how you want to define it. But yes, you can think of it as going backward in time also.
There really is no starting point.
No. But you could, for convenience, say, let's consider all the motions that start out at time t equals 0. Of course, that allows you to start anywheres. It allows you to start anywheres, and so there's lots and lots of trajectories. But yes, they can all also go backward, and you could label the whole thing not label the whole thing, but you could draw the whole entire trajectory, both going backward and forward. An example, just as a simple example, which is too simple for any interesting statistical purposes, a harmonic oscillator, where you have momentum, let's see, position, which did I do it? I guess I did momentum and position. For a harmonic oscillator, the trajectory is just that's not a very good ellipse. It's intended to be an ellipse. The center of the ellipse is at the center of the diagram, and the object and the point in phase space just goes around an ellipse. If you projected it onto the x-axis, the motion would just be going up and down as an oscillator. If you project it onto the momentum axis, which is the same as velocity, it would also be going back and forth. But there are many trajectories. And what distinguishes these different trajectories? The energy of the oscillator. And also where you started them, where they were at time t equals 0. But these are the different trajectories. And as you can see, they don't cross, but that's a general principle. So first of all, there's the principle from classical mechanics that trajectories never cross or merge. Now that's not quite good enough for us. Here's a situation that still could happen even though trajectories don't merge or cross. You could have a situation which in a practical sense is as bad as merging, namely where the trajectories very rapidly come together. They don't quite ever merge, but perhaps they get exponentially closer and closer. All trajectories getting closer and closer. Then for practical purposes, you would lose distinctions. No matter how good your resolving power was, wait long enough and you lose the distinction between these different trajectories, at least from a practical point of view. That doesn't happen. That doesn't happen. Trajectories don't merge like that. Either really merge in this sense or do this kind of thing, which may look to you, but to your eye, the same as this, but you can imagine the difference. Here, trajectories are just coming together asymptotically. That doesn't happen. The theorem, this is called Liouville's theorem. We're not going to prove it. I don't remember if we proved it in the classical mechanics class. It's called Liouville's theorem. Not Louisville, but Liouville. L-I. Liouville's theorem. Liouville's theorem says the following, that if you start with all of the points in a patch of phase space, take all the points in a patch of phase space, start out the system at time t equals 0, and follow each one of them for a certain length of time, the volume of the patch of phase space doesn't change with time. The volume stays the same. That says that even if the points in the phase space might contract in one dimension, they will spread out in the other dimension, in the other direction. And in that sense, distinctions are preserved. The volume in phase space is conserved, and that's the continuous version of the idea that convergence of trajectories doesn't happen. That, if you like, that information is not lost, or that distinctions are not lost. Yeah.
Could you preserve the area, but have it such that it's so complicated that it fills up a huge...
Yes, that's the second law. Yes, that's exactly right. That is the second law of thermodynamics. Well, the increase of entropy is exactly that.
But is that the reverse of this merging? I mean, to say that it's not going to merge, if I
Well-
could put the merge picture backwards, would that give you this?
Yeah, well, we will come to this. This is an important point that, and let me state it for the rest of the class here. The question was, can it happen? And the answer is it almost always happens for interesting systems of sufficient complexity. What can it happen that the volume of this region does stay conserved, but it sort of branches out in some horrible fractalated, I don't know how to draw it. I mean, I'm not very good at drawing fractals. In such a way that it eventually, apparently, fills up the whole phase space. And the answer is yes. The answer is yes, that does tend to happen.
Can a closed volume split into two separate volumes?
No, that cannot happen. It preserves its topology. Yeah, it preserves its topology. There are no mergers, but chaos happens. This is called chaos when this happens.
What's required for this, since it's a theorem, what's the requirements?
Say it again?
What are the postulates, axioms to prove the theorem?
The Lagrangian form of classical mechanics, either the Lagrangian form, the Hamiltonian form, or the principle of least action. Okay? So it all traces back ultimately to the principle of least action, or if you like, Lagrange or Hamilton's forms of the equations of classical mechanics. Yeah.
Does the volume correspond to a known physical conserved quantity?
Yes. Well, yes and no. It's connected with entropy, but entropy is a subtle thing. All right, let me state what the bottom line is. The bottom line is that if we have a system which is enclosed so that it doesn't escape away to infinity, and it has the property, it shares the property with these kinds of systems, the kind of systems that are represented by cycles, namely that there are no mergers and no splittings and that sort of thing, conservation of information, then if the system moves through the phase space fast enough, or in other words, or equivalently, if you weight an average over long enough times, then there is equal a priori probability, subject to the constraints, subject to the constraint of the conservation of energy, which means that you study only surfaces in this phase space which correspond to fixed energy. Fixed energy might correspond to a surface in the phase space, moving around the subspace of the phase space. Then a priori probabilities are simply uniform in the phase space. It's another way of saying that if you time average things over times long by comparison with some appropriate time, then the average over time is simply the average over the phase space, or equivalently equal a priori probabilities to every point on the phase space subject to the constraints. So that provides you, Liouville's theorem provides you with kind of the basic notion of a priori probability, equal statistical weights to every point in the phase space measured by the volume, or every volume of phase space of the same volume has equal probability.
So in some sense, it doesn't have a different density.
Yeah, that's right. The density is uniform on the phase space. The sort of a priori probability density is uniform on the phase space. Yeah.
Are you saying that Liouville's theorem implies ergodicity? I mean, are you saying it's ergodic?
I'm assuming that the system is ergodic. Okay, so ergodic means, All right, so yeah, I'm assuming that. And it's true for almost all systems. Well, actually, I'm actually not assuming it's ergodic. If it's not ergodic, it means that there are extra conserved quantities. When a system is not ergodic, that means that the phase space divides up into different pieces which carry different conserved quantities. Then you have to pick a value of the conserved quantities. So for example, for the harmonic oscillator, that's not ergodic. What does ergodic mean? I'll just tell you very briefly. Ergodic is fairly closely related to chaotic. It's not exactly the same thing, but it means that the phase point wanders around rather thoroughly throughout the phase space and pretty much touches every point on the phase space, very much like this touches every point by the time it gets back. Okay, if it doesn't touch every point, then that means that there are closed sectors which have conserved quantities, which correspond to conserved quantities. For example, this phase space is not at all ergodic. This point doesn't get to every point inside here. It only gets to the points on the same ellipse. But that just tells you that there are conserved quantities. There's a conserved quantity which takes on a value on every ellipse. If you fix that conserved quantity, then you stay on a given ellipse. If you calculate the time average as the phase point moves around that ellipse, that average quantity will be the same as calculating the average over the ellipse. The time average will be the same as averaging over points on the ellipse here. So in fact, really, I have not so much assumed ergodicity as I've assumed when you say there are no additional conserved quantities besides energy, that really is the statement of ergodic behavior. Okay. Yeah.
In your statement of Louisville's theorem, you talk about the volume of the points in the...
In phase space, not in ordinary coordinate space. Not in, okay, so let's just remember what a volume in phase space means is it's a thing with units of, let's say it's a simple particle, one particle. Then a volume in space has units of length cubed. A volume in phase space has units of length cubed times momentum cubed. It's a 6-dimensional little volume element, and it has units of length times momentum, which is called action. Okay. Length cubed times momentum cubed is called action cubed. So it's volume in phase space, not volume in ordinary space.
I was going to say, a point doesn't have any volume.
Right. Well, that's true. Hmm? No. What I'm saying is you start with a little volume in phase space, little or big, it doesn't matter. And you track all the points, and you see where they go. This had a volume, this has a volume. Yeah. Right, but the volume of this will be exactly the same as the volume of that.
In the case of the harmonic oscillator, just the ellipse just stays the same. So therefore,
Yeah.
would that be an example of
But don't you need an infinite number of points to have a volume to show that there's a volume? Otherwise, how can you?
Yeah, an infinite number of points, a volume. Are you fooled by the fact that I drew some points here? Oh no. I just No. It's a continuous infinity. It's a volume. It's a volume in the phase space. I could cross-hatch it. Okay, does that make it better? Better?
Is that kind of related to the fact that you have a one-to-one mapping, so if you have a point in one state,
Yes. Again, the motion of dynamical systems, the initial state at one time is related to the final state at another time as a one-to-one mapping. Right. As a one-to-one mapping, and in that sense, it is like this. All right. Okay. And just as this, if you cycle around here long enough, you will average over all these points with equal a priori probability. The same is true of following points in phase space. And the right statement at the end is that the a priori probability, the a priori measure, whatever you would like to call it, for a dynamical system is volume in phase space. Volume,
Well,
yeah.
let me just point out that you can map the unit circle to the circle of radius 2, and that does not preserve area,
Right.
but it is 1-to-1.
It is 1-to-1. You're right. You're right. That's okay. Good. 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 It's that's right. That's right. It's more than 1-to-1. It's more than 1-to-1. It's volume preserving, or phase space volume preserving, which is better than 1-to-1.
So how do you factor the uncertainty principle into this?
Well, you don't. I mean, we're doing classical physics. Now, if we were doing quantum mechanics, we would subdivide the phase space into little boxes of order h bar on a side, and we would think about little boxes in phase space, which were no better defined than the uncertainty principle allows.
So that actually, from a quantum mechanical perspective, that actually a finite number of points.
Well, a finite density of them in any case. Yeah. Right. Right. Good. And as I said, that's why I don't, at this point, want to. Now, the ultimate justification, in fact, for this principle that of equal a priori probability on phase space really is quantum mechanics. Because it's only in quantum mechanics where the states of a system are discrete and where you can actually count. Where you can actually count states and so forth and make it more like this situation here. All right, that, in any case, that's an important principle that equal a priori probabilities or uniform a priori probability distribution. Let's talk about probabilities and get to entropy. Okay. We've discussed energy. Energy is a conserved quantity. We fix the conserved quantity called energy for a system, and then within the space of a particular value of energy, the system may hop around from one state to another, all with the same energy, and as it hops around, if it hops around fast enough, you get to average, or you get to ask about probabilities by asking how much time does the system spend in each one of its particular configurations. And that, by Liouville's theorem, will pretty much be guaranteed to be just average over the phase space. Okay, the next concept is entropy. Now, you might have thought the next concept in thermodynamics would be temperature. Temperature is much more intuitive than entropy. Well, is it? It's really not. You have, of course, a body sense of what temperature is. Things are hot and things are cold, and so you have I don't think you have an intuitive sense of what temperature means, but you do have an intuitive sense of what hot and cold, or at least a biological sense of what hot and cold is. But it's really energy and entropy which are the more basic concepts. So let's talk about entropy. Okay. Before we talk about entropy, let's talk about probability distributions. If we have some variable, and that variable could be the numbers on a die, or it could be a continuous variable, such as x or p or something else, then you may have a probability distribution of some kind. Where you got it from, let's not worry about where you got it from. This is some variable. It may be a collection of variables. There may be more than one of them, but let's just take a one-dimensional thing. Here's the probability. P goes this way, and the probability distribution, I don't know, it might be like that. at every value of the coordinate or the set of coordinates. By coordinates, I now just mean any parameters which describe the state of a system. As I said, it could be the numbers on a die. If it was the numbers on a die, they would be discrete. And instead of having a continuous function for the probability, you would have just a sort of set of numbers for the probability. The only difference between the discrete system and the continuous system is whereas you might add, whenever you add for the discrete system, you're probably going to wind up integrating for the continuous system, but we'll come back to that. All right. What does it take to be a possible probability distribution? Two things. P must be positive everywhere. In both these cases, negative probabilities have no meaning. It could be 0, of course. When I say positive, I could also mean 0. And the other thing in this case is the sums of the probabilities. Let's call it P of I. I now is which particular state you're talking about. All right. Sum of P sub I is equal to 1. So a sum of positive things, a bunch of positive things whose sum is 1. Clearly, each one of the p's has to be less than 1, less than or equal to 1. If the sum of positive things adds up to 1, each one must be less than or equal to 1. The only way any one of them can be equal to 1 is if all the others are 0. The analogous situation for a continuous variable is that the integral of the probability, let's call this variable x, p of x dx is equal to 1. And of course, the way we use a probability distribution is we don't talk about the probability of a specific value of the coordinate. We talk about the probability that the coordinate x lies between x and x plus dx. We talk about the probability that the coordinate lies in a little interval here, and that naturally brings us to the idea of a probability density. A probability density is a thing that we integrate. A probability for a discrete variable is a thing that we sum. Right? Next concept, another important concept, is the concept of the average value of a quantity. Now, I'm going to assume, of course, that everybody knows a little bit of statistics. Let's take this case here, the discrete case. Suppose that there is some function of I. Let's see, what could we take it to? That could be I squared, yeah. Just some function of I. Well, I could be an integer. I, of course, could be many, many variables. I've drawn it as one variable, but it could be a multi-dimensional space. Some function, some quantity which depends on the state of the system. Could be the energy. It could be anything that you like, any property of the system which, if you know I, you know the value of that property. What do we call that? Let's call a quantity the property f. And f also depends on I. If you know the state of the system, then you know f. What is the average value of f? And we'll label the average value of f by just a notation, standard notation for averages, standard physicist notation, bracket around it. That's the average of f. What's the definition of the average? The definition is to sum up over all I, f of I, but weighted with the probability for that value of I. Remember, the p's add up to 1. That's the definition of the average value of a quantity. And it is the standard average. It's the ordinary average, except weighted by the probability, not just by a flat measure, not just adding up the f sub i's and dividing, but weighting them according to p of I. Why do you weight it according to p of I? Well, you can imagine a situation, for example, where you had only one non-zero probability, you wouldn't want to, if you wanted the average value of f, it's quite clear the average value of f is just the value of f at that point. If you look at this formula, that's what you'll get. All the p's are equal to either 0 or 1 in this case, and you'll only get one contribution. So that's called the average. And now what I want you to imagine, as I said, I do want you to keep in mind that there could be, this space here could be a multi-dimensional space of some kind. But I've enumerated all of the states of the system here. I've enumerated them all, laid them out here. And let's suppose now that all we know about the system, the only thing we know is that it's in one of m possible states. Let's suppose there are n states altogether. M is less than n. And all we know about the system is that it's in one of these m states. So it could be this set of m states over here. That's all we know. What is the probability out here? 0. So the probabilities are 0 out here. What about out here? And what about in here? Not 1. 1 over m. Remember, they have to add up to 1. So this is m states in here. All we know is that it's in this range here. And the probability in here is 1 over m. Question? When I say we know nothing but, that's another way of saying they're equally probable. Yeah. If we know nothing but the fact that it's in one of these m states, that means, and we really just don't know anything else, then it's equally probable that it's in any one of these m. Okay? If it's equally probable that it's in any one of these m, a statement of a complete ignorance is equivalent to the statement that all things are equally probable. Right. So a statement of complete ignorance, other than that we know that the system is in one of these m states, is equivalent to saying that we have a probability distribution. Let's draw it over here, which is 0 everywhere except in this range where the probability distribution is 1 over m. Right? Okay. This m here is a measure of our ignorance. The bigger m is, the bigger our ignorance. Now, why might we be ignorant? There may be many reasons for being ignorant, but the usual reason is because the number of degrees of freedom, first of all, they're very microscopic. Second of all, they're very numerous. And so typically there's lots and lots of ignorance about a system. And all you know is some restricted information. Now, in this case, I've drawn a very, very idealized version of that idea where I know nothing except that it's in one of these 1 over m states. M is a measure of your ignorance. But is it the only possible measure of your ignorance? No, you could take m squared, you could take m cubed, you could take any monotonically increasing function of m, and that would also be a measure of your ignorance. The one which is called entropy is the logarithm of m. Okay? Logarithm is a monotonically increasing function, log m. It's called S. S for entropy. Why is S entropy? I don't know. Is logarithm of m for this particular case over here. It's logarithm of m, or if you like, it's within this, well, okay, it's logarithm of m, which is also equal, incidentally, notice that it's equal to minus logarithm of 1 over m. The only reason I'm writing in terms of 1 over m is because the probability distribution happens to have height 1 over m. All right? So this is writing it in terms of logarithm of the probability distribution in here. Logarithm of the probability where it's not 0 in a non-zero range. That is a measure of your ignorance. Yeah.
Does it matter what the base of the logarithm is? It's a natural logarithm?
Yeah, we're going to, in fact, you have your choice about how you want to define it. And in different branches of science, it's defined in different bases. In physics, it's always a log to the base e, natural logarithm. In information theory, it's usually log to the base 2. But the conversion factor is just a factor of logarithm of 2. Right? The logarithm of a, yeah, so it's a trivial relationship. In information theory, people like using binary digits, and they like taking powers of 2. An entropy of logarithm of 2 is called, well, logarithm of 2 in this sense, in the natural log 2, is called 1 bit. We'll come to why it's called a bit, but in any case, this is the entropy. Now, why take the logarithm? I'm not going to tell you right now why we take the logarithm. The answer is because it's useful to take the logarithm. What's that?
You just told us.
Yeah, I'm not going to tell you why it's useful. Yet. We are certainly going to find out why. All right, I will tell you. I will tell you. Yeah, all right, I will tell you by example. Let's do an example. Supposing I have a bunch of coins. N coins, big N coins, N coins, each of which can be heads or tails. That's my system. My system is not a single coin. My system is N coins. Heads, tails, heads, and so forth. Okay? And supposing I know nothing about it, let's take the most extreme example of ignorance. I don't know nothing. Okay? What's the entropy? Well, how many configurations are there altogether? 2 to the n. What's the logarithm of that? N log 2. Notice that the entropy now is proportional to the number of coins. It makes sense now to talk about the entropy per coin. The entropy per coin is logarithm of 2. By taking the logarithm, we reduce entropy to something which is additive, which adds up over the system, which is proportional to the size of the system, for example. The entropy in this room is proportional to the number of molecules in the room. But the only reason that it's proportional to the number of molecules in the room is because I've taken this logarithm. So here's an example. If the molecules were just replaced by coins, and the only question was, is the coin a head or a tail, you can see that by taking the logarithm, you make something which is proportional to the number of degrees of freedom. So entropy, like energy, is something which adds up for systems. Yeah?
And in base 2, that's just n.
Say it again?
In base 2, that's just n.
Yeah, in base 2, that would just be n. Good. In base 2, it would just be n. In base e, it's n log 2. But in any case, in either case, 1 bit of information means either, when we're talking about base e, it means a entropy of log 2, or when we're talking about to the base 2, it just means an entropy of 1 unit. The entropy of a single coin, if we didn't know whether it was heads or tails, that's called a bit. So entropy is measured in bits. Yeah.
Is there a precise definition of degree of freedom? I mean, I sort of know
Yeah.
what you mean, but
A variable.
how do you know how many degrees of freedom something has? I mean, just-
Well, you ask how many variables are there that you have to know. In this case, the variable is either head or tail, head, tail, and you need to know n of them. I imagine we can concoct some more official definition, but I can't think of it right
More or
offhand.
less, in your example, you're getting the number of particles, because that's kind of just flowing through.
Well, in the case of a single particle, of course, it's 6, the 3 coordinates in the right. So more or less, yes.
Yeah.
Wait a minute, you said we know zilch in this case, but you didn't take that into account.
Yeah, but in this case, we don't know zilch. In this case, we don't know zilch. Right. Right.
In the case of Hume's law, if you double the number of coins, then you double the entropy. So that would be an argument for using the law with it, because
Yeah, that's the idea. That right. 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 Now, an exercise you could ask is, supposing you did know the zilch, then what would the entropy be? Then there would be some states, right, right.
Then you take averages. Then you do one more thing. If you know something is additional, you know the probabilities, you take an average of that log quantity.
Absolutely. That's called, yeah, absolutely. Well, we're going to take an average of this quantity. Yeah, precisely. Precisely. But you got me so excited with that remark that I forgot my train of thinking. No. It was a tremendously important point, and I forgot what it is. Well, I don't remember what it is, but let's just do a couple more examples. Again, supposing, I remember what the important point is. Supposing we know everything about the system. Knowing everything would mean, in this case, we know exactly which configuration we're in. That would mean that one of these states has probability 1, and all the others have 0. What's the entropy then? 0. It's just log of 1. Log of 1 is 0. Okay? E to the 0 is 1. So this is a kind of interesting fact. When you have complete information that's equivalent to 0 entropy, when you have no information, that's when you have the maximum entropy, incidentally. You cannot have an entropy bigger than this. This is easy to prove. Logarithm of n. This one is the largest entropy you can have for that case. So entropy is a measure of ignorance. Now, this is interesting. Notice that with this definition of entropy, and it is the real definition of entropy, it is not really a function of the properties of a system. It's a function not only of the system, but your state of knowledge of the system. Now that sounds a little bit ridiculous, because entropy is something we're going to treat as though it were a quantity associated with the system, and we'll come to why. But really, it's a joint question of the system, its probability distribution. In fact, it's a function of the probability distribution, is what it is. Okay, so that's the simple-minded notion of entropy over here. Now let's try to find a definition going exactly in the direction that you pointed out a moment ago. Let's imagine some probability distribution. I don't mean it to be continuous. I just don't want to draw a bunch of vertical lines. A probability distribution now, which is not flat and then 0, but may have some width, maybe close. It may be that it's close to 0 in some region, in some range, and then close to 1 for some other range, and then close to 0, but it's not exactly 0s and 1s. It's a more complicated, or arbitrary, in fact, probability distribution. Can we generalize this idea so that we have a measure of ignorance, which is in some sense approximately a notion of the number of states that we've included under the probability distribution here, which have non-negligible probability, the logarithm of it. All right, so here's the usual definition. It's actually the average. The average, here it is, log of 1 over m. It's the average of logarithm of the probability. The average of the logarithm of the probability. Now, wait a minute. Minus. Remember that the probability is always between 0 and 1. What does that mean about the logarithm? Negative. Just like the logarithm of 1 over m is negative here. So that means that this is positive. It's the average of the logarithm of the probability of the ith configuration. Okay. How do we calculate that? Well, we just use the formula for averages. Where do I have the formula for averages? I think I lost it. So let's write it down. The average of a function of I is equal to the sum over I of f of I times p of I. Let's apply that. Let's calculate the average of the logarithm of the probability. That's equal now, for f of I now, we just substitute minus log p sub I. So what is it? It's just summation over I of minus p sub I, that's this one, times the log of p sub I. That's called, this is it. This is the final definition of entropy. Let's look at it for a moment. Supposing we have one of these distributions which is flat and 0, equal to 1 over m up on the top, and it encloses m states altogether. What is this quantity? Well, outside, when we start adding up the contributions to it, there are contributions from the regions where p is 0. They give 0 because p is equal to 0. On the other hand, there are the contributions from within this range. And what are they given by? They're given by, let's see what they are. P sub I is 1 over m for each one of those states. Then there's logarithm of 1 over m, a minus sign, and now we have to sum over I, but each one of the states in this bin here gives the same answer. So what do we do with it? We multiply it by m. We multiply it by the number of states here. That just cancels out this and gives us minus log 1 over m, which is the same as log m. So this formula, the average of the log of the probability, reproduces this formula for a square distribution like this, but it's more general. And it is kind of a measure of the width of the distribution, or the number of configurations with non-negligible, more or less equal non-negligible probabilities. But it is what it is. P sub I log P sub I is called the entropy. Okay. As I said, it reproduces this answer when the conditions are applicable for this answer, and otherwise it gives a general answer. Any questions? Yeah.
Don't you have to add in a coefficient of Boltzmann's constant to make it consistent with classical thermodynamics, in which you have...
Boltzmann's constant.
Pardon me?
Boltzmann's constant.
Yeah.
Absolutely. Yeah, I always forget about Boltzmann's constant. Right, okay, so let me right. Boltzmann's constant traces back to the definition of temperature. Energy and entropy together determine temperature. In the early days, when physicists, or whoever they were called themselves at that time, steam engineers, whoever it was, were interested in temperature, they really didn't know what temperature was. All they knew was how you measure it with thermometers. In the beginning, they didn't even have the idea of an absolute zero of temperature. But today we know temperature is a form of energy, or is measured in units of energy. The appropriate idea of, for example, the temperature of a gas is a measure of the energy of individual molecules. Not exactly, but that's roughly what it is. The conversion factor between energy, which was measured in joules, and temperature, which was measured in degrees, Celsius or degrees Kelvin or whatever, the conversion factor was not known. It wasn't known how much energy per molecule there was in a gas at a certain temperature. So there was an unknown conversion factor. Boltzmann introduced it. He was the one who realized, Boltzmann and Maxwell, realized that at least for a gas, or an ideal gas, temperature is a measure of the kinetic energy of the molecules. But the unknown and why was there an unknown conversion factor? Basically because they didn't know how many molecules there were in a mole of gas. They knew how much energy, they could measure how much energy does it take to heat up a mole of gas 1 degree. But what they didn't know is they didn't know how many molecules were there. So Boltzmann's constant, which was a measure of the energy per molecule, that was unknown. If we use, today we know, of course, how many molecules there are in a mole of gas. And we can work, if we like, with units of temperature, which are really just units of energy. We can measure temperature in joules. It's just the energy needed, the energy of a single particle, roughly speaking, the energy of a single particle in a gas at that temperature. So that's just a historical fact. Boltzmann did not know his own constant. Boltzmann was so depressed by the fact that he didn't know his own constant that he committed suicide, and I think the next year Einstein figured out what Boltzmann's constant was from the Brownian motion. Yeah. I don't think that's the reason Boltzmann considered suicide. Did suicide. I don't know why he did. Newton also didn't know his own constant. Yeah. Yeah. Took many years for Newton's constant to be measured. It took a few years for Boltzmann's constant to be measured.
Did Planck know his?
Yeah. Yeah. Planck knew his. Yeah. Absolutely.
Can we partition the constants? Can we partition the constants? Those constants where the person whose name is attached to it knew what the constant was.
How many constants are there? Let's see, there was one of the hard ones that took a little bit of time was the electric charge. What was known and easy to measure was the ratio of the charge to mass. And then it took some time until, what's his name, figured out, no, not Michelson, Morley, Millikan. Millikan figured out how to measure the charge separately from the mass. So whoever thought of the idea that electrons had electric charge didn't know the value of the charge. Right? Who was that? Who was the first one who postulated that electrons had charge? Or that there were electrons and they had charge? Yeah, I think it was Benjamin Franklin. No, I think it was Benjamin Franklin. I don't think it was Ronald Reagan. I think it was Benjamin Franklin. I don't know where that came from. What?
You said Gore, I can understand.
Bohr invented the electron. All right, so we have now the concepts of temperature and entropy. and I've introduced the idea of a probability distribution. Now, we're going to go further next time, but for today, let's just postulate something called thermal equilibrium for a system. Now, let me first explain when a system can be said to be in thermal equilibrium. These are not necessary and sufficient conditions. This is necessary condition. But for many systems, it's sufficient. For lots of systems, this is good enough. Thermal equilibrium is not a property of an isolated system. If you have a truly isolated system, it's not in thermal equilibrium. It has an energy. It has a very definite value of the energy. You may not know what it is, but it has some energy, and that energy is fixed. Thermal equilibrium is a property of a system in contact. I'll tell you what contact means in a minute. A system A in contact with a much bigger system, B. A doesn't stand for anything. This is not Alice and Bob. This is A and B. A just stands for the system under consideration. B stands for heat bath, bath. It's a very big system with many, many more degrees of freedom. And the whole system, the whole combined system of A, the thing of interest, and B, the heat bath, has a given total energy. That's an assumption. For our purposes, the bigger system can be thought of as a closed and isolated system. Let me say what closed and isolated means. It means there's no way for energy to flow into it and out of it. Either it's contained within insulating walls that don't allow any heat energy in or out, or it's just an isolated region in space that nothing can come into or out of. The bath plus A can be an isolated system, but A is not an isolated system. Now, if the bath is big enough, basically in the limit, one other thing. The bath plus A is isolated, but neither A nor the bath themselves are isolated, but they weakly interact. Weakly interact means that the energies of interaction, whatever the interaction between A and B are, it's governed by some energies of interaction. The energies of interaction are very small compared to the energy of either A or B. But the interactions, whatever they are, allow energies to go back and forth from A to B. They allow energies to be transferred back and forth from B to A, from A to B. The whole system has a definite energy. So the whole system has a definite value of the zilch being energy in this case. That whole system will move around in its phase space on a surface of constant energy, but it'll move around and hop around from point to point to point to point. And among other things, the different points will correspond to different ways of partitioning the given amount of energy into the energy of the heat bath and the energy of A. So under these circumstances, neither the energy of the heat bath, which we're not terribly interested in, nor the energy of A, which we are interested in, will have a definite predictable value. It will fluctuate. It will have a probability distribution. A probability distribution, if you wait long enough, just wait long enough, that's it. I mean, there's some time scale. Of course, if you start the system in some arbitrary way, it won't be in thermal equilibrium. But if you wait a long time until it equilibrates and energy is hopping back and forth between them, in a long time average sense, there will be a probability for the energy of A. Okay? and in other words, the various configurations of A, let's plot them. Here are the various states, the energy states of A, values of the energy. This is energy now. They may be discrete, they may be continuous, not important for us at the moment. These are all the various values that the energy of A, this is the energy of A that it can take on. We start with a given total amount of energy. Okay. The energy of A will be a small fraction of it, but as a function of the total energy, there will be some probability distribution, and we can also think of it as a function of the average energy within A. Whatever the energy of the whole system is, there will be, the bigger the energy of the whole system, of course, the bigger the energy, the average energy of A is likely to be. So we can parameterize the nature of the system by the average energy in A or by the total energy. If we know one, we know the other. If we know the total energy, in principle, we should, if we know how to calculate the average energy of A. We'll learn how to do that. All right? So the average energy of A or the total energy, either one, but let's say the average energy of A, this is the average energy of A, or just the energy of A, has some probability distribution, and this probability distribution is a function not only of the energy of A, but also the average energy of A. If you give me an average energy of A, then there will be some probability distribution. So let's just think of a probability distribution which is parameterized. In other words, it's a whole sequence of different probability distributions. The different probability distributions correspond to different values of the overall energy. Yeah?
The average of A is taken over time, or?
Yes, it can be taken over time. Yes, it's taken over time. The average energy of A is taken over time. All right, so it's parameterized. You have a probability distribution, which, in fact, we can just say it's a function of the state of A and the total energy, if you like. The total energy parameterizes the probability distribution. Change the energy, you change the probability distribution of A over its states. The states of A are I. All right. Here are two things you can calculate if you know the probability distribution. You can calculate the average energy of E of A, and you can calculate also the entropy. Given a probability distribution, you can calculate the entropy of A. Just entropy of A, which happens to be the average of the log of the probability of A with a minus sign. In other words, you can calculate the average energy and the entropy. Now I'm going to tell you what temperature is. What temperature is. If you increase the energy of the system, of the combined system, if you increase it, needless to say, and obviously, the energy in A will increase a little bit. If you increase the energy of the whole system a little bit. In general, the entropy will also change. The entropy in A will also change if you increase the energy of the whole system. And you can ask, how much energy, how much change of energy in A does it take to change the entropy by 1 bit? How much change in EA, how much change in the energy of A must you make in order to change S by 1 bit? What is that? That's the change in energy, the derivative of the energy with respect to the entropy times that 1 bit, which is logarithm of 2 or something. This is not the important thing here. That's how much energy you have to add to A. And how do you do it? You add the energy to A by adding it to the whole heat bath here. That changes the average energy EA. And how much must you change EA in order to change the entropy by 1 bit? In other words, to hide 1 more bit of information, to increase your ignorance by 1 bit of information. How much energy do you have to put into A? This derivative, the change in energy per unit entropy, is called the temperature. That's what's called temperature, T. It's the energy change needed, if you like, to state it colorfully, to hide 1 more bit of information. But technically, it's the change in the entropy per unit entropy of the system. Okay. So from an information theoretic point of view, it's the change in the entropy if you hide an extra bit of it. An example of it, incidentally, is Landauer's principle in computing, that if you want to erase a bit of information from a computer, now remember, you can't destroy information. You can't destroy information because it's conserved, because of the principle of conservation of distinctions. So if you try to erase a bit of information from the computer, you wind up putting it into the heat bath surrounding the computer. All right? How much heat or energy do you put into the heat bath by taking 1 bit of information out of your computer and putting it in the heat bath? Well, it's the temperature times logarithm of 2. That's the amount of energy, that's the amount of heat energy that you put into the environment when you erase a bit of information. That's an example of it. And that's why you can't erase information from your computer without putting heat into the environment. Why? Because when you erase a bit of information, you change S a little bit. Well, you can see why. You can see why.
There are people working on reversible computers.
Yeah. But if you, yes, right. That means you do your computation without erasing. Right. But if you erase, you will heat the environment. Yeah. Right. What's that? I missed the.
You can heat your house by erasing your information.
What you can't do is cool your house by opening the refrigerator.
But a bit is really a small amount of energy in terms of like an environment that you would be in.
Yeah.
Right.
Right. Okay. So let's say now where the smallness comes in. The smallness comes in for exactly the reasons that were asked to me a few minutes ago. What happened to Boltzmann's constant? And the answer is, really strictly speaking, Boltzmann's constant goes here, KB. I'm inclined to work in units. Just like when I do relativity, I work in units in which C is equal to 1. When I do thermodynamics and statistical mechanics, I always work in units in which the Boltzmann constant is equal to 1. But in ordinary units, which are what? They're joules per degree. K is joules per degree Kelvin? Yeah. Right. Right. It's a terribly small number. What is it? Anybody remember? 10 to the minus 23. Right. Like Avogadro's number. No, inverse of Avogadro's number. Right. So it's a very, very small number. And this means when you erase 1 bit of information at a temperature T, this temperature, incidentally, is the temperature of the surroundings. When you erase a bit of information, you change the energy of the surroundings by a very small amount. So K is a small number. And yes, and it's also true that entropy the standard thermodynamic definition of entropy, let's see, what I call entropy differs from the standard entropy also by a factor of a Boltzmann constant, but is it upstairs or downstairs? I forget.
Isn't that a little bit of a circular definition, since in order to define S, you have to enumerate the states?
What's that again?
Isn't it a circular definition
Which?
that one bit of information is erased if, under that situation, since in order to define S, you had to enumerate the states, which means that you enumerate the bits.
Well, I don't think it's a circular statement to say that if I erase a bit of information from the computer, it heats the atmosphere by a certain amount.
Well, in order to define S, you've got to...
In order to find F, which is F?
S, the entropy.
Which?
S.
F, yes. Right.
And if you enumerate the states, then you enumerate the bits.
You don't have to know anything about the computer. You don't have to know anything. You don't have to enumerate the states. You don't even have to know what the states of the system are. It's just a general fact that if you erase one bit of information from any computer, no matter what its states are, and no matter how it's made and what company it's made by, it will always heat the atmosphere by that much. So is it a circular statement? No, I don't think it's a circular statement. Look, statistical mechanics is in a certain sense a bunch of tautologies. It's mathematics. Okay? When we apply it to physics, we're adding something else in. And we're adding in this idea of averaging over times and so forth. But I didn't want to get into Landauer's principle of what happens when you erase a bit of information. I simply wanted to give you the definition of temperature. Temperature is the change in the energy that you must add in order to change the entropy by one bit, which means divided by log 2.
When we were thinking about the die and thinking, well, we're only interested in one face, okay?
Yeah.
We were making a choice about what information was considered relevant, okay? And it's not necessarily the same thing that the computer user thinks of as a bit that causes the chip to get hot. So that's a different bit. They're probably related by some constant. I'm saying that chips that have lots of cells get hot.
Yeah, but
Period.
that
There's a
once
certain amount of
that's
energy
something
that
else.
we would call a certain amount of entropy. Okay? But that's not the same thing as what in the computer you would call a bit. Because there's
There's a lot of other stuff going on.
right.
Yeah, no, the actual statement, the correct statement of Landauer's principle is you will heat the atmosphere by at least this much. There's a very idealized situation where only this very, very simplest thing happens, namely, without disturbing it any other way, you eject one bit. Landauer's principle said that's the absolute minimum that the energy of the atmosphere will change by if you erase a bit of information. So, yeah.
Is the numerator, is the numerator E the average
Yeah.
energy
Yeah, the average energy of A.
of A, so it should really have a bracket?
Yes, it should. And I'm going to get tired of writing the average. From now on, whenever we think about a quantity associated with a subsystem here, I will often neglect to write average. But when we're thinking about the subsystem in equilibrium with the bath, what we mean by the various quantities associated with it is the averages. And they fluctuate. They do fluctuate. And we're going to talk about calculating fluctuations. Fluctuations are an important thing. In fact, it's what Einstein realized Einstein realized that, that the quantities of thermodynamics fluctuate. Right? He realized that those fluctuations would have effects on small little impurities in the system and knock them around. And what he did was essentially calculate the fluctuations using statistical mechanics, fluctuations of various quantities like pressure and energy and so forth, and demonstrated how they would affect small impurity in a system. Okay, we've done quite a bit. We've gotten energy, entropy, temperature, phase space. All right, the next time we will work out and derive the Boltzmann distribution. The Boltzmann distribution is the probability distribution for the states of A in the heat bath. And it's obtained statistically by using some probability arguments about energy being transferred back and forth between the system and the giant heat bath. Okay.
For more, please visit us at stanford.edu.